I greatly appreciate this opportunity. I'm really excited to tell you about this project. We are about 2.5 years into a 5-year project, so we are running it full bore right now. So this webinar today is really an overview of the project as a whole, and then telling you some of the individual parts where we've made the most progress, and those are what will be highlighted in some of the subsequent webinars after this in the following weeks. So I'm going to be talking about research you can use on water research, on water conservation, recycling, and treatment. But to really convey how we've gotten to where we are now, I really have to say I've been building on the backs of giants. We have had 2 other projects that have helped lay the groundwork for much of what we know, both about irrigation and managing irrigation and nutrition via distributed sensing. That was a project that was funded by the USDA Specialty Crops Research Initiative. And this is really your tax dollars at work, And then we also have the project that was managed by Xuan Hong at Virginia Tech, Irrigation, Pathogens, and Water Quality, where he was looking at really how plant diseases move and survive in ponds so that he could better help us manage pond water quality to mitigate the potential for problems from pathogens in water. So our project, this SCRI Clean Water, Reduce, Remediate, Recycle, is really looking at water when it's applied to the pot and as it runs into the pond, and how we can reduce, remediate, and recycle water and contaminants. So Philip mentioned that there are a lot of collaborators working on this project. We have 9 institutions from all over the country. We have 21 co-PIs, and if you've heard of the expression herding cats, that is exactly what goes on, but this is an amazing team that works very well together, and we are getting a lot of good work done. But really, those getting the work done are our research team members. We have over 22 research team members working on this project, from undergraduate students to postdoc research assistants and the like, and they are the reason that we can actually get this work done. So I just want to say that, and many of these are people who will be working in the industry in the future and will be making our industry viable in the future, at least the educational components of it. And then last but not least is we have grower collaborators working with us who have partnered with us, who are allowing us on site. These are both greenhouse and nursery growers, and they allow us on site to monitor water, to monitor whatever is within that water, whether we're just talking about pH and how we manage pH, or whether we're talking about diseases, pesticides, and they're really helping us to fine-tune many of the technologies I'm going to be talking about today, so that we have pilot scale and full-scale applications of these technologies, so that by the end of the project you will be able to potentially visit some of these sites and see the technologies we've been talking about and talk with actual growers who have applied and used these technologies. So the overall project goal is to encourage recycling of irrigation runoff. And to accomplish this goal, we have a whole slew of objectives. But realistically, that which binds it all together and makes it work is we're developing online tools. And these online tools that are going to be hosted at cleanwater3.org. Again, if you look at that bottom right-hand corner of your screen, you can see that link. Eventually, all of these tools will be posted on that website, and we're creating this basically one-stop shop that you can go and you can look and you can determine what you need based on the problems or the solutions that you're looking for based on your operation. And so it ranges not only from how you reduce water use, which helps reduce agrochemical and disease presence in runoff, to evaluating runoff treatment technologies so that we can clean the water, with the goal of water recycling. And when we talk about water recycling, the first knee-jerk reaction tends to be, is there stuff in my water that's going to hurt my plants, that's going to make it harder to grow the plants? I don't even know where to start. Why? What? How do I treat? Is this going to be a consistent supply of water? Is it worth the cost? And in thinking about all of these questions, those are the questions that we are developing answers for, and we'll integrate those answers so that you can feel confident in any decisions that you make. But we fully recognize that there are barriers to recycling water. And I mean, these could be actual or perceived, but you know, that top barrier, whenever we brought this up with growers, when we surveyed growers and talked with them in person, it was diseases in the water. We do not want to recycle diseases in water and infect new crops coming in because there were diseases present in the water. What happens if there's pesticides in the water? And a pesticide, I simply mean it could be a plant growth regulator, an herbicide, an insecticide, a fungicide. That's just an overarching class of chemicals. And we think about this, and I'll take an example, like a PGR. If you have a PGR, Paclobutrazol in water, residuals of PGRs in water can be relatively high. And in this example on that bottom left corner of the screen, in the spring, most of the samples had more than 5 parts per billion of Paclobutrazol residues in waters. And if you look at that picture, if you have more than 5 at 10 parts per billion, that begonia crop is much smaller than at 5. So there are potentially detrimental effects of having pesticide residuals in water. And then, so how are we going to mitigate that? And then we think about nutrients. Now, I know some of you are going to say, I want the nutrients to stay in my water, and I understand that completely because that's basically fertigation. But if you're an open pond system where your water body is open to sunlight, oftentimes when you have high concentrations of nutrients present in water, you may have unwanted plant growth, whether that's algae, duckweed, other aquatic weeds, any of these, and these impact both pond chemistry and what you're going to have to do to treat your water to remove diseases, as well as just simply pump clogging. So there are some reasons why managing nutrients before they get to your pond are well worth the effort. So, and to understand some of these reasons for applying different technologies that we talk about, and you'll notice in the top right corner of my slide I say webinar number 4. So I'm giving you some very brief glimpses of what these next series of webinars will actually be talking about. So if you're really interested in the topic that I'm talking about and you see that little banner, that means there's another opportunity for you to hear more about this, and that you should sign and come back during that week so that you can find out more about it. Okay, that was my digression. But, so we have reasons for technology use. Some of them, and they range and they differ among people and groups and where you are and who you're communicating with, but some of these in the basics, and this is definitely not my area of expertise, but relative advantage. So why do we want to do it? So it comes from stemming from the desire to just protect the natural environment, or it could be increased social prestige, or it could be decreased long-term financial costs. But then if you think beyond just that relative advantage to how it will integrate with your operation compatibility, technology is ever more being integrated with almost everything we do every day. So it is a new norm. So how do we think about growing plants and integrating technology? Do we look for early adopters who apply it and are the ones who do the trial and error and figure out why it works? Do we look at how that technology fits and complements what we currently do on site? Does this technology help us save time, which in turn results in labor savings? How complex is the technology? Can we trial it, or can we go to another grower who has it on site and see how it works for them? All of these are different reasons for technology use, and you will be able to hear more about them in that 4th webinar. But when we think about reducing, or the reduce component, realistically that first parameter that comes to mind is irrigation. So if we can reduce irrigation or optimize irrigation on site, then that may in turn lead to reduced disease pressure, reduced pesticide residuals present, and reduced nutrient losses. And I'm going to give you some examples of each of these. So if we think about reducing production input inefficiencies, so water is applied and 30 to 80% of it is actually used. And sometimes, so to translate that, that means that 20 to 70% of the water applied by most operations is actually not used by the plant and runs off that that production area. And when you have that much water running off of a production area, if you've just applied an insecticide or a fertilizer, that might also mean that you're having a good proportion of that pesticide or fertilizer actually running off. So if we look at that pesticide number, 10 to 67% actually stays at the container where you want it. That means, what, 33 to 90% of that pesticide can move out of the area where you want it, which means it's not doing what you want it to do. That's a lot of loss, and if we can manage our irrigation to help mitigate that, that might save you some serious money. As well as if you think 30 to 60% of the nutrients are used, that means 40 to 70% are not. That's a lot of money that's going out of your container and going into your water and potentially moving off-site. So if we can manage these more efficiently, we are in a much better place. So what this can mean is that it can be a simple solution. I know I usually get eye rolls when I talk about irrigation audits and looking at enhancing irrigation practices to manage water better. But one of the simplest solutions to reducing the amount of water waste is conducting an irrigation audit, where you go out there and you put some catch cans out and you run an irrigation cycle and you see how uniform that distribution is of irrigation across your production area. And then if it's not uniform, you adjust your heads, you clean the heads, you replace the sprinkler heads, and you can affect a lot of change and save water and more uniformly irrigate your plants, which may in turn mean that your plants look better and perhaps finish sooner. But from the simple, you can also get to the bit more complex if we're talking about irrigation timing and volume, and looking at where we have an example of at an operation in Maryland where there's two production beds. So if you've seen the green box and the blue box at the bottom sort of center of your screen, the green box represents grower-controlled irrigation, where it's just based on time and their experience of how much they need to water throughout the day. And then that blue box is sensor-controlled or substrate moisture content-based irrigation practices. And so a trial was done with two beds side by side of chrysanthemums in 2015, where they had the grower or the timed irrigation versus the substrate moisture sensor controlled irrigation. And so I know this is a sort of busy slide, but what I want you to kind of concentrate on first is total water use in gallons. So if you look at that substrate moisture sensor controlled column and look at it over time, you see ranges from 14,000 gallons applied to 141,000 gallons applied in August. And if you look at timed versus grower controlled, you see a very similar range. But what you'll notice is that there's some instances in some months they have irrigated less, and in some months that sensor-based irrigation actually irrigated more. And what we attribute this is to their actual, the sensors able to detect when the plants have consumed the water in the substrate or absorbed the water in the substrate, and they add more water, so those plants may not have some just incipient stress. And so I realized that some of this may not look like a lot of water savings. So you saved about, 30,000 gallons, but that's on one bed. So if you multiply that by the number of beds that you saw in that previous picture, that could be a lot of gallons of water. And depending upon where you live, that could be a lot of money. But if we translate that to what the plants looked like, the plants were very, very similar. There was no different than height, width, or depth. But this example is for a very conservative crop where the grower that we worked with did not want to risk under-irrigating their crop. If we look at another example, this is with a grower in Tennessee, and they had a very similar setup where they had sensor-controlled versus grower-timed irrigation, but they conducted this work with both Dogwood and Red Maple. You can look at, so if we look at Dogwood time, total water applied was 29,000 gallons per row. With the Dogwood with the sensor controlled, it was 10,000 gallons per row. That's almost 20,000 gallons per row difference. And if you look at water savings, that's considerable when you multiply that over the many rows of trees that are grown. And you can, and so species dependent, these sensor controlled systems and soil moisture based systems seem to be very efficient and can save money. And so what that translated to for these growers is that they pumped less, so they saved $8,000 in pump cost. And management savings, they were turning a lot of valves to turn the irrigation on and off. And with this system, they said that with reducing the amount of time that they were investing in it, that saved $20,000. The sensor system cost them $15,000, so in the first year they had an annualized net savings of $5,000. And depending upon where you live in the U.S., Tennessee is probably the cheapest water you can get because really your only cost associated with water are pumping costs. In California, it's $1,000 an acre foot, so there's a lot more incentive to be more conservative just based on where you live and what your water costs and what your water source is. So we've talked about irrigation. Now we're going to talk about savings in fertilizers. So some of the work that we're doing, I think they would argue this is preliminary work, but it's a really exciting look at this. So at Virginia Tech, they're looking at your conventional application of a controlled release fertilizer, where at that bottom right pot where it's incorporated throughout. And what they've simply done is they said, we want to incorporate that rate into the top half of the pot. So if you look at those three containers on the left, you have a half rate, 3/4 rate, and full rate, but it's incorporated in the top half of the pot. And why they thought of this was that because when you stick a liner in a pot, generally it's only in the top half of the pot. And if you're irrigating over time, it may take 2 weeks to a month or longer for those roots to grow out into the bottom of the pot, but by that time the water has contacted the fertilizer prills that have been incorporated throughout, and you've lost a good portion of your fertilizer to the soil, just to leaching. And so they validated this with various crops. For a holly, it didn't matter how you did it, they all looked about the same. For a hydrangea, the top half incorporated versus the full incorporation, they looked about the same. The 0.75 in the top half was slightly smaller, but what this could translate to is hydrangea is a heavy feeder. So if you put it all in the top half, perhaps the plant gets more of it, or the growth can be more refined within that system. And they're looking at a few more species, and they're performing these evaluations at growers and in different geographical regions, and you probably hear more about this. So if then we translate from the irrigation practices to from fertilization practices to now to thinking about disease and reducing disease. So again, looking at that same system where we had the sensor controlled versus the timed settings. So the sensor controlled are the blue bars and the timed settings are the green bars. I mean, generally, if we ran statistics on these, the number of plants that were symptomatic would be very similar. And in some instances, they were more, but they're all very similar. So even if we're using a sensor to control irrigation, these plants are not any more likely to be infected than they were using traditional. But Johanna and Cass are going to talk a lot more about this in our next webinar and how you manage diseases caused by Phytophthora and Pythium. And you'll learn much more in depth about how they're doing this and some of the other studies that they're working on. And we're also thinking about disease hazard analysis. So you have an operation and you want to know where your hot spots are. So where do you need to worry about? What do you need to monitor? So we've worked with several of the growers, our grower collaborators, one in Oregon and one in South Carolina, and we've gone to their site and sampled, and we've looked to see if there's any hot spots present. And then once we have this sample, we can then get a guesstimate, or actually it shouldn't be a guesstimate. We can actually give you a good percentage of what pathogens or disease organisms are present. Is it Pythium or Phytophthora? Are they harmful? Are they not harmful? And what sort of risk is associated with them? And then if you look at that bottom graphic, where in that operation do we think that major problem is, and where? Is it at the pond? Is it at the pump house? Is it after a sand filter or before a sand filter? Where do you need to concentrate a treatment technology to actually manage that disease so that you reduce your risk on the rest of the operation? So these type of scenarios will help with that. So again, if we sum up sort of that reduce component, we think about if we manage irrigation better, it can help us reduce runoff, which in turn probably means that we're reducing leaching. And if we reduce leaching, that might mean that fewer nutrients leach from the pot. That means that you're getting more fertilizer to stay in your pot where you want it rather than having it leach out. Then we can think about pesticides. Perhaps your pesticides stay at their point of action longer, and so they can be, so their residual effect can be longer. And disease organisms, if we can optimize our irrigation to minimize what we can with regard to how diseases move on site, then this in turn, if we combine all of those, makes remediation easier. Because when you reduce, you have lower volumes, you may have higher concentrations, but it makes managing, cleaning that water a slightly more simple prospect. So I break out contaminants that we're really concerned with in production into two different categories. We have physical contaminants, which are usually sediment, bark or peat, plant waste, algae, and I have pesticides in the wrong column, and then biological contaminants, which are nutrients, pesticides, and diseases. And these are sort of some of the treatment technologies and how their mode of actions works to remove contaminants. And so if we talk about physical contaminants, we have pretty much, there's probably a few more that we could talk about. The ones that we're actually doing some work with and ground truthing and making sure they work and quantifying how they work really rate from rapid physical filters, which really work to remove large organic materials from water, bark, peat, algae, that kind of things, to filter socks, which you see that green sort of tube installed in a ditch, and this is basically something similar to see what you would see in a construction site where they're trying to manage sediment. It's the same principle. What these are designed to do is that production runoff flows through those filter socks, but stormwater runoff can run around them and over them. And then that really works very well for sediment, but sediment also helps to move phosphorus and pesticides and potentially diseases on site. So managing sediment helps you manage some of the other contaminants as well. And then we also have granular activated carbon as a physical treatment, and these can work for pesticides, PGRs, and color. And I mentioned color because color could be a proxy and help you determine how well your filter is working, relatively speaking. And then if we talk about the biological treatment technologies, we have floating treatment wetlands, vegetated buffers, a carbon wall, and a mixed bed bioreactor. And I'll be talking about each of these a bit more as we move along so that you're more comfortable with the terminology that I'm throwing at you. So if we break it down to nutrients, some of the treatment technologies that work to remove nutrients from water are floating treatment wetlands, vegetated buffers, filter socks, the mixed bed bioreactor, and carbon walls. Because of the time that we have and also the stages of research involved, I'm really only going to talk about floating treatment wetlands as with relation to nutrients for this section of the talk today. And so what's a floating wetland? So if you look at that graphic on the right, it's a very clear picture. You have plants that float on top of the water, and you have little cups that get inserted into a mat, and then the roots grow out of those cups, and those plant roots are actually within the water column, and so you have a greater surface area of plant roots in the water column that can help filter water and absorb nutrients. But what also those plant roots do is provide a surface area for microbial communities or biofilms to form. And these biofilms or sticky microbial masses actually help trap particles and absorb nutrients from the water. So it is really a very complex living system that works to treat water. And you'll say, so how well does it work, or why should I even think about it? Why should I even think about it? So when we talk about floating treatment wetlands, generally we do want to talk about nutrients, because if you're in the Chesapeake Bay or Florida or in California with a pond that you're worried about overflow, or any of the other areas where there are environmental nutrient total maximum daily loads or other environmental quality parameters related to this, floating treatment wetlands are a technology that you can install on existing infrastructure. You don't have to invest in digging other constructing a new technology. You already have that infrastructure there if you have a pond or a lined ditch of some sort. But how well do they work? So, and this is relative, and I should probably have this in comparison with others, but Juncus effusus, which is a soft rush, if you had an acre of plantings, you could remove 148 pounds of nitrogen, and that was when we had a 12 parts per million exposure concentration, and that's about average over a year, or your median concentration in runoff over a year, at least for a nursery. Greenhouses would be quite a bit higher. If our phosphorus level, that loading rate, were about 3 parts per million, we'd be able to remove about 16 pounds of phosphorus per acre. Ponaderia cordata, which is a pickerel weed, which has beautiful purple flowers, you could remove 862 pounds per acre and 106 of nitrogen, then 106 pounds per acre of phosphorus. So if you think about cost benefit, where you can put this technology, you can get an idea of how small or large it has to be to remediate what you need. And what really the floating treatments do is they compete with other plants. So they're going to compete with your algae, they compete with your duckweed, and potentially they help ameliorate some of the effect of and reduce algal blooms and duckweed growth on ponds, as long as you're managing these floating treatment wetlands. And when I say managing them, I really mean harvest. Because if you don't harvest these systems, the nutrients that are absorbed by the plants and fixed into their shoots or to their roots will be simply recycled over winter as those plants senesce. And so what can we do with that? We are currently working on looking at if one can harvest and then plant into a container and sell, or harvest and then plant in direct plant for restoration purposes and perhaps riparian zones along streams or lakes, anything along those lines. And we have our first year of data on that, and it's looking very promising. So, or one can compost the material. So there's a variety of things that one can do and remove nutrients, and this is really focused on cleaning the water so that you have fewer shifts in pH, but also have fewer aquatic weeds, or to just help minimize potential for release of nutrients off-site where they don't need to go. If we talk about pathogens or diseases, and we can talk about floating treatment wetlands again, and vegetated buffers, which I think almost most growers could use vegetated buffers for this technology. But again, irrigation volumes. We're just getting back to simple managing irrigation to help manage pathogens or diseases on site. So I'm really going to focus in on the vegetated buffers part, and what I'm really going to talk is what I like to term as designer filter strips or inline filter strips, where you are intentionally selecting plants that are not susceptible to infection by Phytophthora, so that you can hopefully clean that water, remove Phytophthora propagules, and not have a host that is re-inoculating your water. So what we have done at Clemson is, over the past 5 years now, we have been screening multiple aquatic plant species that survive in these wet ditches that have irrigation runoff flowing through them. And we have, and the ones that are on your screen right now are those that, at least at the first blush, and we're rerunning these this summer, are not actually infected by species of Phytophthora after they've been exposed for a range of 15 to 30 days. So what this means is, if these plants are not as susceptible, their roots are not infected, that these plants should be ideal candidates for then further, pardon me, placing them in vegetated buffers or in floating treatment wetlands, and using these to help filter and remove that contaminant disease from the water. So if we move to treatment technologies to manage pesticides, I have 3 listed here, and this is where I'm going to sort of get into some of the nitty-gritty of these technologies so you're familiar with it and you're a bit more comfortable. Carbon walls have been used for quite a while now, but they have typically been used for removing nitrogen from big ag and other areas, or for wastewater treatment plants. And basically a carbon wall is simply you dig a big ditch that's sized based on the amount of runoff volume you have and that needs to treat. You fill it with a bark or a wood chip, and then you cover it back over and you let water run through it, and you have designed it for a particular retention time, and basically a microbial community grows within there, and in the conditions there, nitrogen is removed from the system. Your mixed bed bioreactor is somewhat similar, but instead of a carbon substrate within it like a carbon wall, you actually have, if you look at that right picture, and then there's an inset with what look like little plastic wheels. Those plastic wheels are what provide the substrate for microbial communities to grow on, and you can remove nitrogen within these systems as well. And then we also have activated carbon or charcoal filters. And what we're really anxious to see is that can these systems remediate pesticides? This is still in the early stages. And then if they can, are these communities damaged by the pesticide presence? Because if you have some fungicides or some of the other chemicals in there, do they influence it and reduce the efficacy for other contaminants, for removing other contaminants? So if we look at the carbon wall or a mixed bed bioreactor, as the guys at Michigan State are talking about, they have a two-stage system where they have a carbon wall and then they have another substrate which is targeted at phosphorus removal, but they are applying a pesticide to their production bed and then letting that runoff run through these systems to treat it. The mixed bed bioreactor on the right is looking at both nitrogen and phosphorus removal, and phosphorus is very difficult to remove from water bodies. So figuring that out, but then also looking and then spiking with another pesticide to determine if these communities are inhibited or help to remove the contaminants is what's currently going on. So not this year, but probably next year or the following year, we'll have some really interesting information on these. And pesticides are one of these things that regulatory agencies are becoming particularly concerned with in runoff. And then if we talk about recirculating and cleaning paclobutrazol, you remember that one of the first slides I showed where the begonias were impacted by only 5 parts per billion of paclobutrazol. Oftentimes when you're recycling water on site, if your chemical is very water soluble and wants to stay within the water, it will be easy to recirculate. So how do you remove it? So guides at University of Florida, and you're going to see more about this in webinar number 3. I apologize, I have number 2 there, but it's number 3, and how do leading growers solve water quality issues. But so on site, this grower installed a daisy chain of granular activated carbon, or GAC. And so if they only used one of them, if they only pushed water through one of them, it could treat 17 gallons per minute. If they pushed it through all three, they could treat 50 gallons per minute. And their minimum contact ranged from 3.3 minutes to 10 minutes. And then how well did it work? It worked very well. So if you remember that our 5 parts per billion was our sort of magic number that we really wanted to get below, and bioassays also, where you use a plant as a proxy to determine if a chemical is present, also showed similar to this. So if you look at the purple line, which is the top line that has much more magnitude in it, pre-filtration concentrations ranged from, as little as 0.25 to as high as 72.5 part per billion paclobutrazol. And then if you look at the red line with the squares, the minimum was less than the detection limit to a max of 3.3. And again, these were all lower than limits desired to not have an unintended effect of that PGR on crop growth. So paclobutrazol removal with granular activated carbon is very effective. So what does this really mean? So at the end of this, when we talk about whether we're talking about a pesticide, a disease organism, or a nutrient, what we want to give you are options so that you can go, sort of like you'd go to the grocery store and figure out what you need. You can come here, you could look at a treatment train of options for best management practices. So whether you started with carbon wall, sort of at that top left, the brown with dots on it, or whether you selected a vegetated channel or a constructed wetland or a floating treatment wetland or sediment catch basins or filter socks, or instituted a treatment train of ponds, all of these are considered different best management practices, and some of them you've probably already started to use. But how you use them and what order they're put in, all of that, we're going to have that information so that you can make informed decisions on which technology might work best for you based on your particular operation, your flow volumes, and so that you can make, again, just informed decisions. And along with just the scientific or the data on efficacy, we're also going to be presenting sort of the economics of this. So we've also have a carbon footprint we've had of, and a carbon footprint is just looking at basically inputs to a system and where those inputs and which sector they break out in, and I'll show you that on the next slide. But we've performed these, we've developed these for both West Coast boxwoods and East Coast boxwoods and trees and such, and they're working on a herbaceous material model right now. But what this translates to is that for your different scenarios, which factors most influence production cost? How much that container, that single management unit costs. And you can see which factor influences cost most. In this example, it looks like it's labor and equipment, basically, at transplanting that are some of your greatest costs. But then you can think about, if you're wanting to make a change in practice, which of these categories will that affect, and is that going to move your cost more to the right or to the left, or higher or lower, and it will help you make an informed decision. But also we want to present this information to you in a way that is logical. So if you've got feedback on what we're proposing right now, because this is sort of our prototype of what the website will eventually sometime look like, please feel free to drop me an email. I would greatly appreciate any input. But basically what we want to do is break out different components of a production system, and then there will be sort of tools associated with each one. So if we picked out sanitation as what we wanted to focus in on, the folks at University of Florida and Texas A&M have done a great job of evaluating some of the sanitation chemicals, and both chemicals and filters out there currently used. And if you look at it and look at this system, so if you have an operation that you have low flow volumes, it may not cost as much for you to install a system. But if you have a lot of high volume of flow and lots of water moving through your system, it may cost more to install, but it'll cost less to operate. But you can look through each of these and it's sort of, and see which one you might be interested in, and see installation cost and operation cost, and make an informed decision on what you might want to work with. If we take it a step further and look at water as the production system, and really focusing in sort of on the recycling aspect of it, we'll have case studies on the site that you can go look at and see. And I mean, this example has been highlighted multiple times in our industry newsletters, and it's because it's such a darn great story, talking about success in stewardship. So, and it's obvious, Altman Plants, they installed a water recycling system, they installed a new pond, a very large pond, pond liners, infrastructure, all of that. It cost $900,000 to do it. They were able to find grants and rebates totaling $653,000. So realistically, they spent about $350,000. And based on the cost of their waters and how much water they use, 460 acre-feet a year, they saved $460,000 in their first year, which means after their investment, they still saved $100,000. And that is considerable, considering they are growing in Southern California where their water is limiting. So they are being touted both in, nursery news and as well as in the media there, simply because they are a poster child for when something goes well. We also have a tool that helps you with tracking water quality on site. So GroZone Tracker, and you can, if you typed it grozonetracker.com into your web browser, you would come up to this site. And what this allows you to do is you can register your company, you can have multiple users at your company, and you can pinpoint a particular bed. So you'll notice that red dot there, that's pinpointing a particular bed, and you can have pour-through readings on a plant, and you can track the EC and pH over time, and it will tell you if your crop is staying within a designated range that you've selected, or if you're veering out of it, and then you can figure out that you want to manage it sooner rather than later before your plant hasn't been growing well. Or you can put in water quality readings whether from your pump or your pond or wherever it was, and track water quality over time so you know what your water quality will be or have a better idea over time. This is just a tool that's simply to help you manage and track over time. Realistically, we want to help you. We weren't going to provide economics. We'll have efficacy data for treatment technologies. We'll have case studies. We'll have these tools that allow you to use that so that you can figure out how you want to manage your production inputs to reduce the agrochemical and disease loads. Determine which treatment technology or BMP might be best for you to use to remediate any of these so that you can begin to move into that recycling irrigation runoff and not impact the quality of your plant's growth. So again, this is the website I've been talking about, cleanwater3.org. This is what it looks like right now. We are envisioning, once we have more tools developed and we're in our we're moderately moving along at this stage. We're probably, well, we have quite a bit of work to do here. But what it will eventually look like is that same diagram that I showed you, where you can click on that and figure out related to water, disease, substrates, whether on your computer or on your mobile phone, and you can see and look through and figure out some solutions for any problem that you may have. And so at this time, that was the very quick, dirty overview of the project, and I hope I've piqued your interest in that you'll come back and listen to some of the other webinars over the next few weeks.